Hello everyone, my name is Chen Chen, and today I'm going to present the work we accepted in CVPR 2018. It's a joint work with Wakwas and Dr. Mubarak Shah. The work in this paper is real-world anomaly detection in surveillance videos. So the surveillance video has been increasingly used in the US. So shopping mall, other public spaces, and if you go to, actually I've been to the Orlando Police Department, their monitor room. There's a lot of monitors, surveillance cameras, but there's just not many people, police officers there to look at those monitors. So oftentimes, if you find there's anomaly, if there's no person watching the video, you will miss that. So develop an intelligent algorithm, to automatically analyze those videos and flag those anomalies to the officer. Then the officer can, take actions when the anomaly happens. So this will save a lot of time and a lot of labor. So anomaly detection, here's an example. In the right, there's actually like a child kidnapping happening. So here you will see the anomaly score will go up very high. The 1 means the anomaly score is between 0 and 1. 1 means there's a high chance there's anomaly happen. So if we set a threshold here at 0.5, then the system will generate alert. So there is a possibility something is happening. So the officer should go there, go to the field and to check that out. So that's the goal of the developing an automatic system, to detect the anomaly in video. So there's a previous approach to do this anomaly detection. So the straightforward way is that you can develop some classifier to detect specific anomalous events, for example, traffic accident. So we can, train a classifier to specifically detect traffic accident. But there's a problem is that it cannot generalize to other, anomaly events. So if you want to detect other events, you have to train a separate classifier. And there's also sparse coding based approach, which assumes the initial portion of the video is the normal portion and use that to build a dictionary and reconstruct the future frames. If there's anything deviates from the reconstruction's error is very large, then it considers there's an anomaly happening. So this approach does not able to handle the environment change very well. If there is a sudden drastic change of the environment, there will, result in a very large reconstruction error, and will possibly produce a high false alarm rate for different normal behaviors. So for our approach, the goal is to identify the time window of the anomaly in the surveillance videos. And we use the normal video and anomalous video to learn the anomaly pattern. So because the anomaly has a lot of patterns, and you cannot specifically list all those patterns. So we use these normal anomalous videos to try to learn distinguishing between these two. And in our approach, we use the weakly labeled training video. That is, for those training videos, we know which video is normal and which videos are anomalous. That is, we only know the video level label, but we don't know where that anomaly happening. So the anomaly can happen in any time in between those long surveillance video, but we don't know where it is. We use the weakly labeled videos that if you do those segment level annotation, it will take a lot of time because you have to go through the video as a pinpoint which time it happens and which time at what time it ends. So for the weakly labeled video, we use the multiple instant learning approach. So we divide those anomaly videos and normal videos into segments. Here we use 32 temporal segment, and we construct a bag. So for the anomalous video, at least one of the temporal segment will be corresponding to that anomalous segment. So we call it a positive bag. And each of these temporal segments is a bag instance. And for the normal video, because none of them will be corresponding to any anomalous event, so it's called a negative bag. So if we have the segmentation level annotation, which is label intensive, so the approach we'll do is we just have a ranking loss, which this FVA is the anomaly score of the anomalous segment will be higher than those anomaly score of those normal segment. But here we don't have those segment level annotation, and we only have those bag level. So what we do is, in the multiple learning framework is we, in the positive bag, which is the anomalous bag, we find the maximum score of that segment. So this one, the highest anomalous score in the anomalous bag, which is most likely will be a true positive instance, right? Because that's the anomalous segment. For the negative bag, we also find the highest anomaly score in the instance of that normal bag, which looks like an anomaly event, but it's actually not, because we know it's coming from the normal video. So it's a hard instance. So we want to the maximum of the positive score will be larger than the maximum score from the negative bag. So that's the multiple instant learning framework ranking loss. And we use the hinge loss formulation for the ranking loss, and we also further impose two constraints. One is the smoothness constraint. That is, those continuous segment anomaly score should be not deviate too much, because we want those score to be predict scores should be smoothly increase or decrease. And also the sparsity constraint is that we don't want too many spikes, those spikes in the prediction score, because there will be some of the false alarms. So we impose these two constraints in the multiple instant ranking loss function. So here is the overall anomaly detection framework. So we have those anomaly video and normal video. We divide them into segments, temporal segments, and we construct those positive bag and the negative bag. Then we use the C3D feature extraction framework to extract the features from those temporal segments. And we predict the score for each of the segments. And we enforce the multiple instant learning ranking loss. There's some existing data set for anomaly detection, but there's some limitation of these existing data set. First of all, they contain some simple anomalies, wrong direction running, and sometimes they were staged and they were contain unrealistic anomalies. For example, here the UCSD data set, they consider the skater and wheelchair consider them as an anomaly in the on the campus, but in real world this should be as a normal situation. And videos are often captured at one location. So for our data set, we collect 1900 realistic real-world surveillance video from YouTube, and about 128 hours. And the data set is 15 times larger than the existing data set, and it contains 13 real-world anomalies. And here's the number of video, the distributions of each anomaly category. And we also have 950 normal videos. So here are the sample video examples for the normal events. So they are strictly CCTV camera videos. And here's the example of the anomalous events. Okay. So we did the experiment by constructing training set with 800 normal and 810 anomalous videos, and we test that our algorithm on the rest of videos. And here's the result of our anomaly detection algorithm. So as compared to the other state-of-the-art method, which is sparse encoding and deep autoencoder method, our method outperforms them significantly. And I'll show you some of the anomaly detection examples of our method here. So again, here's the left is the anomaly score from 0 to 1. The higher means there's a high chance there's an anomaly happening in the video. And we also test on some of the normal video because oftentimes the surveillance cameras will capture some normal scenes. You don't want a system have high false alarm rate. So and our algorithm works very well on the normal videos as well. And we also want to demonstrate the generalization ability of our approach. And we test our trained anomaly detection algorithm on some unseen anomalies. So the BOSS dataset, which contains some anomalies which are totally different than our dataset. So we use our trained model on our dataset and directly test on the BOSS dataset, to see how the method can generalize to other unseen anomalies. And compared to other algorithms, our method again performed the best. And here's an example for the unseen anomaly detection, which I showed in the very beginning. And the child kidnapping was never example trained in our dataset. And it is still able to pick up, where it happens. And we also because we have those 13 different anomaly events, we also conduct action recognition result. So we can train some action recognition classifier and test, to perform some action recognition experiment and see how challenging is the data set. So we have two different algorithms. One is the C3D method and the TubeCM method in our group. And the accuracy is pretty low. The reason is that the video is the surveillance video, which is very, very diverse and oftentimes low resolution, and is a long and untrimmed video. So it has pose challenges for action recognition algorithm. And here the confusion matrix of these two methods. So in summary, we have developed anomaly detection algorithm just using the multiple instant learning framework with weakly labeled data. And we collect a new large-scale anomaly data set, which consists of a variety of anomalies, which is from the real world. And our proposed anomaly detection method can outperform the existing method significantly. And our dataset can also be served as a benchmark for action recognition and can open some more opportunities for future work. And here's the dataset, which is publicly a website for the dataset. And you guys can check these websites out and download the dataset for testing. All right, thank you.